Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 797, all paths from source to target. This is a medium level difficulty graph problem, and we're told that we're given a directed acyclic graph of n nodes labeled from 0 to n minus 1, and we need to find all possible paths from node 0 to node n minus 1 and return them in any order. So in this example, n is we need to find all the possible paths from 0 to n minus 1. N minus 1 is 3, so basically the last node in the graph. And we're given what is essentially an adjacency list. So each index is the node itself. So node 0 has two adjacent vertices, 2 and 1, and so on and so forth for all the other nodes in this graph. So we're given an adjacency list, which makes things a little easier, and we need to find all the possible paths from 0 to n minus 1. In this example, in example 2, we can see 0. So we have 0 to 4, which is one path, 1 to 4, which is another path, 1, 3, 4, 0, 3, 4, 0, 1, 3, 4, and 0, 1, 2, 3, 4. So there's multiple different paths in this example, and we're given some constraints, and we're told that the input graph is guaranteed to be a directed acyclic graph. So there are no cycles, and it's a directed graph. So let's hop straight into the code. So let's we want to use kind of like a backtracking depth first search approach for this problem. So we want to have our result variable, result list, which is going to store all the result paths, because remember, we need to not only return the number of paths, but also we need to return the actual paths themselves. So the result is going to store all the paths, and let's initialize our depth first search function. It's going to take in a node, and it's going to take in the current path we have so far. And what we want to do is append our current node that we're at. So let's say we start off at node 0. We want to append 0 to our path, and we want to say if the node is equal to the length of the graph minus 1. Well, we've found our destination node, which is n minus 1. So we can append a shallow copy of our path to our result list. We want to make sure it's a shallow copy because we don't want to mutate it when we carry on backtracking. And then we want to say for each neighbor of our node, so for each neighbor in graph, and pass in our in graph and pass in our node like this. We want to do depth first search on that neighbor as well as the path. We need to also pass in the path that we've created so far, and then we can say path.pop. So we backtrack. So after we've got to our destination, we can then backtrack and bubble ourselves back up, and then do the depth first search on the other neighbors and the other paths as well. And once we've popped from our that's our depth first search function done. So then we can call depth first search function on 0 and pass in an empty list. And once our depth first search function has completed, our result will contain all the paths from the source to the target. So let's submit our code and let's check everything works. And it does. We pass all 30 test cases. In terms of time complexity, we're looking at a big O of p times v plus e. So p is the number of paths, v being the number of vertices, e being the number of edges, and the space is going to be O of n, big O of n, because of the call stack. So I hope you guys enjoyed this video, and with that being said, I will catch you in the next one.